Good afternoon, everybody. My name is Charlie Nicklin. I'm the Chief Executive of IAgrE, and I'd like to thank you all for joining our presentation today. Today, I'd like to welcome Richard Farnish, who is the Technical Director at the Wolfson Centre for Bulk Solids Handling Technology in the University of Greenwich. Richard is a chartered engineer and has been at the Wolfson Centre for 26 years. He has actively engaged in providing consultancy services in both the UK and overseas in the storage and handling of bulk materials. Just before Richard starts, you're all currently muted. If you'd like to ask questions, please use the chat function at the bottom of your screen, and then at the end of the presentation, we'll unmute you so you can ask in person. Okay, over to you, Richard.
Thank you very much. And of course, one of the delights of these sorts of meetings is that you don't have to waste 10 minutes going through fire evacuation details and where the smoking points are. So that's always a plus. Great stuff. Okay, so what I've got for you today is just a sort of an overview, as it were, about materials handling or bulk solids handling problems that afflict not just the agricultural sector, but also the more sort of processed foods and, you know, problems that are pretty much prevalent everywhere. So to start off with, I don't know how many of you are familiar. I guess some of you, a lot of you probably are, with the writings in the 14th century of a guy called Dante, who wrote a poem called the Divine Comedy, within which he talked about the 9 circles of hell. And here we have it. So this is representation of the 9 circles of hell, according to Dante, from the 14th century. You'll notice that we've got the descending circles down into hell. And of course, what I've done down here is to update it for your benefit with the modern way of thinking. And that is that actually the final level before you get to hell is normally, for most people, bulk solids handling. And bulk solids handling, of course, relates to the storage and movement of could be grain material, could be processed materials. The problems are the same pretty much whatever sector you might care to think about. And of course, when problems are arising with handling of materials or trying to get materials to flow out of equipment, normally you'll find it's quite easy to pick out where those problems are developing. With this being a common sort of scenario in industry, where we can see a vessel that hasn't been flowing particularly well, and the operators have chosen to give it a little bit of gentle persuasion to get the material to come out. And again, you can find this sort of thing happening on small vessels right up to silos, with the only difference being, of course, with small equipment, the operators might opt for hammers, whereas you'll find as the equipment gets bigger, it's not unusual to find lengths of scaffold pole being applied, or in some extreme cases, believe it or not, front end loaders being used to, inverted commas, nudge the silo. So in all cases, it doesn't really seem to matter what scale of operation you're running with. The chances are that at some time or another, you're going to run into some sort of an issue with either getting the material to come out, or stopping it coming out in some cases, or having a material that when it comes out, it's got lumps in it where material has sort of undergone an early stage of fermentation. Or perhaps you'll find that when it comes out, you'll find that the material is nominally quite clean at one stage of the discharge, but then becomes progressively more dusty at different times during the discharge. So, you know, for most reasonable people, if they were to look at a process where materials are being stored and discharged, you know, the first thing they probably notice is there's this large cylinder which has got a cone section on the bottom of it. And for many engineers, that tends to be about the extent of the consideration as to actually what that piece of equipment is and what it actually does. So normally things like stores, whether they're buffer stores or storage silos, are merely considered as a means of holding material before you then discharge it. So there's nothing particularly special. It's a funnel with a barrel section on top. What's the big deal? Well, that's what we're going to be looking at. So, you know, if I talk to plant engineers and I say to them, look, I need to understand more about your process. Can you just, you know, sketch out for me how your process works and what sort of goes on within it? And the chances are that I'll be presented with a really simple flow diagram like this, where step one might be materials into a process, step two might be sifting or milling, step three might be blending, and step four might be bagging it off into 25 kilogram sacks or into cubic meter big bags, or it might be you're filling a road tanker or whatever. But essentially, you'll find that when engineers are asked to describe a process, not unreasonably, they think about it in terms of the steps or stages in that process. And of course, when they're doing that, what they're actually describing are the value adding steps of the process. You know, normally, if you take delivery of a raw material, the whole nature of business is that you'll do something clever with that material to improve its value, and then you sell it into the marketplace or into the supply chain, and make a profit. Sounds pretty obvious, really. So most engineers, even plant designers, have a very solid focus on the pieces of equipment within the process that increase the value of the product. Now, that's all very well and good, because the amount of understanding that is out there that relates to these value adding steps is not only very extensive, it's also typically very accessible. So it means that if you're looking to improve the operation of your plant, it's quite easy to predict the payback on investment over a length of time, because you know exactly how the machine's going to perform. And it could be you're putting in a larger mill or a larger sifter, so you can increase the throughput. So it's easy to make these justifications for an appropriate level of investment. Now, at the moment, there's nothing there that's a big surprise to anybody. You know, it stands to reason. That's what engineers are paid to work out. However, what we're sort of covering today is the connecting lines. And so what the connecting lines actually represent is what we call bulk solids handling. So that's where you've got a material being handled in a large quantity. And it could be it's going into a buffer store, and then it's being extracted and moved on within the process. So these lines actually are bulk solids handling. But the problem that industry typically faces, insofar as productivity or wasted materials, these are not normally directly associated with the process steps. And you'll find that typically the main causes of inefficiency and wastage in process plants comes from the bulk solids handling. And one of the problems here, of course, is that for most engineers, their understanding and experience of bulk solids handling is largely based on experience gained through their careers. Most engineers have not had the benefit of a formal education in the subject of bulk materials handling. And it means that when equipment is being specified or tendered for, the big unknown is, how's it going to work? And is there actually a payback on investment? Unfortunately, you can't answer either of those questions in most cases. The will it work question is normally dealt with by the process guarantee that anything that you buy is accompanied by. But the payback on investment, you simply you can't make that argument or justification because it doesn't add value. So you often find that the bulk materials handling that's applied into process plants is pretty much typically bought down to a price. Because at the end of the day, if everything you're buying has a process guarantee attached to it, then arguably, no matter what you buy, it's risk-free. The reality in many cases, though, is that when problems do develop, from experience I've had in companies, the process guarantee simply means that the supplier will come back on maybe 3 or 4 occasions, tell you that this equipment has been used in many sites with no problems at all, and the fact that it's not working at your installation to the level that you want is actually a problem with your material, not their equipment. And unfortunately, for most people that don't have much of a background in the subject, it's a hard argument to counter, because you would expect the suppliers to be the expertise base in the field. But unfortunately, you find that in most cases, the expertise that the suppliers have has also been gained through a long period of trial and error with designs. So they know what works for the majority of cases. But when it gets down to special considerations, you often find they start to flounder a little bit. So the real problem that you're faced with here is that bulk solids handling doesn't add value. But, and you probably guess what's coming next, is of course, if it doesn't work properly and these connecting arrows are not fully functional, then you then create bottlenecks in the process that prevent the value adding from happening as efficiently as it should. Or in some cases, if we're looking at handling a material after it's been blended or granulated in an extreme case, then you'll find that the materials handling can actually deblend the material and or damage the particles and degrade them. So there's a lot of value removal that these systems are quite capable of delivering. But normally that is not considered at the time when the purchasing decision is being made, because you've got the guarantee. So the way to think about this is that virtually everything in bulk solids handling is usually bought down to a price rather than up to a standard. And the consequence of that, of course, is that the money that you save on a piece of equipment is often the benefit that is completely lost in the ongoing operating expenditure to either keep the equipment working or losses through out-of-spec materials. So it's very much a case of you get what you pay for. But the unfortunate thing is that because bulk solids handling is seen as a very sort of, no one's really quite sure what subject it is, because it's not maths, it's not physics, it's not chemical engineering, it's not mechanical engineering, it's not process engineering, it's a bit of everything. And the consequence of that is that most universities don't touch it as a subject in the context of how industry needs to be informed. So it means that it's very hard to make a good decision with regards to what you're actually buying into. So just talking about things at a basic level, because clearly I'm not aware of what your particular backgrounds might be. If we think about liquid inside a container, and we can quite easily work out what the pressure is that's acting at any point in that column of water. It's simply rho GH, something that we're all familiar with, because at the end of the day, most engineers have had formal education when it comes to things like fluid dynamics, and that goes across many subjects. So liquids we can understand. In fact, most people understand liquid behavior reasonably well. Now, where people get into a bit of trouble is when we start to talk about powders or granular materials. Because now, whereas with a liquid, you've got the density of the liquid and you've got viscosity or your main concerns. When you start to talk about a mass of particles in together, you've got internal friction between those particles. So you don't have viscosity, you've got friction. But also you've got friction between the particles and the surfaces that they come into contact with. So what this means is if we consider a comparable volume of powder to liquid, and then we look at the stresses acting inside that column, we'll find that it's not linear in any way or form. You've got a pressure distribution like this. So this is predicted through the Janssen equation. And what this shows you is that the pressure is non-linear, but also it shows you that about a third of the total downward load acts sideways. So that's the horizontal load going into the walls. That's the vertical load acting through the column. So we can see that wall friction has an important role to play insofar as how these powders are going to behave in storage. And the greater the wall friction, the greater the amount of friction that will be taken away from the base of the silo. And conversely, if it's a very low friction wall, then you'd be increasing the loads at the outlet. And of course, by varying the loads at the outlet, that's then when you get into implications for things like the torque settings for the torque and power requirements for, say, an auger feed or something like that. So bulk materials are a completely different thing to work with than liquids. They're far more complex. And unfortunately, for one reason or another, it tends to mean that bulk solid materials are often considered to be difficult to work with. And that's often based on looking around at comparable organizations where you'll find they've got exactly the same sort of problems that you've got. So, you know, bulk solids get a bad rap. So thinking about bulk solids, well, we can look at discrete particles quite easily. We can get the shape, we can get the size, we can get the surface texture. We can take photographs of them. That's all quite easy stuff. When we look at the bulk solids, then we've got to understand how those bulk solids work together. And it's an entirely different behavior than you would think from discrete particles. So in the bulk form, we've got free flowing particles. So these generally tend to be coarser particle sizes, which have relatively low forces of attraction acting between them. So to give you an analogy of this, you know, if I took a handful of granulated sugar, squeezed it into my hand, and then released my grip, then that sugar would drain out between my fingers. So basically, free-flowing materials means you can put a pressure on them. When that pressure comes off, the material goes back to its uncompressed form and it moves freely. The second form is where we have cohesion. This is where we're now down to finer particle sizes where the forces of attraction are stronger between them. So now instead of thinking about granulated sugar, we'll talk about icing sugar. Get a handful, squeeze it really hard, release that grip. Some of the sugar runs off between our fingers, but often you'll be left with a little lump in the palm of your hand. So cohesive materials, when they have a stress applied to them, they actually change their characteristic. So they gain strength from having a stress applied to them. So fundamentally very different behaviors, but they're all bulk particulate materials, but clearly very different behaviors. So you would think the equipment would look quite different that you handle these through. However, if we just have a quick look around the internet, and these are some pictures I pulled off a couple of months back, and let's just have a quick look at like something as simple as the shape of the cone on a vessel. So here's a cone, 60-degree cone. So it's 60 degrees measured from the vertical. So 60-degree cone. Let's see what else we can find. Oh, here we go. 45-degree cone from the vertical. Look a bit further. 30-degree cone from the vertical. And essentially, with those three geometries, that's pretty much the range you'll ever be offered for anything. Now, at this point, were we face to face, I'd say to you, well, where do you think those angles come from? And I hope I'd get a range of probably overthought answers that are quite intelligent. And unfortunately, you'd all be wrong. The geometry that you see there, and the clue actually is in the angles that are picked, lies in how draftsmen used to make drawings, which is with a 30-60 set square or a 45-degree set square. So a lot of the none too cheap equipment you're buying actually has its geometry based on a set square with absolutely no consideration at all for the materials that you're working with. And that is a major problem. And this is where a huge proportion of industrial problems come from, is simply the fact that the equipment doesn't bear any consideration at all for what you're going to put in it. So the consequence of this is that when you come to discharge equipment, so in this case, we're showing a conical vessel. When you come to discharge, you'll find that if it hasn't been designed for the equipment, but has simply been built to a standard geometry, you'll find that the flow channel will tend to propagate up from the outlets, interface with the top surface, and then material from the periphery starts to drain down. So in effect, what you've enforced there is a first in, last out stock rotation. Now, clearly, you know, if you're talking about the storage and discharge of a harvest, that's not too much of a problem because you'd be draining this down to empty. So ultimately, it all comes out. Because where it's a problem is if you actually got a vessel as part of a process and you're topping it up before it drains down, so you don't make the process run dry. And of course, by doing that, it guarantees that the material down here is in there for a very long time indeed, which gives it plenty of opportunity to start to ferment or to form agglomerates or adhere onto the convergence of the bin. So there's a lot of bad things happen through a lack of consideration of the flow pattern. Now, don't get me wrong, this flow pattern is appropriate for probably, I don't know, probably about 80% or more of materials handled in industry. But to apply it as a blanket condition across all types of handling operations is where the problems come from. Because for some materials, an operating state is totally unsuitable. So common flow stoppages, mechanical arching, this is simply where the outlet is undersized. Normally, to avoid mechanical arching, it's something you would associate more with like aggregates more than agricultural products. But generally speaking, it means that the outlet needs to be 6 to 8 times the diameter of the largest particle size you'd expect to arrive at the outlet. It's a fairly easy one to design away without knowing too much about the materials. But cohesive arching and rat holing are both functions of materials that have a degree of cohesion derived from higher fines content or through segregation effects. So cohesive arching and rat holing need to be designed away by using an understanding of the flow properties of the materials that are going to go through that bin. And both of these are a combined function of inappropriate conversion angle and inadequate outlet size. So if we look at fairly standard sort of agricultural type arrangement where we've got eccentric outlet silos, Again, for putting a harvest in, storing it, and then taking the entire harvest out, really not too much of a problem at all there. The eccentric outlet arrangement is simply so that you get a vertical wall on one side of the outlet. And the concept is that if you get a bridge or an arch forming, then because you've got a vertical wall there, it means the arch will lose strength and you'll get flow initiation fairly easily. But if you use this style of vessel in a process where you're topping it up, then what you'll do on the more shallow angled side of the bin is you'll create a substantial long-term residence period, and you can then reasonably expect to have issues with lumped material coming into the flow channel and cross-contamination. So something to be mindful of. But again, it proves the point that a vessel is not necessarily intrinsically wrong. It all depends how you're going to use it in the process. So here we've got different styles of pyramidal bin. This is being used with aggregates. That's the bin on the left-hand side there, being used with aggregates. Free-flowing material. The fact that it's first in, first out makes no odds, because clearly being an aggregate, it's not going to go off with time. It'd be very unfortunate for it to form any solid lumps in there, because this will be graded roadstone. So no problems at all with that geometry. But here we can see a steelworks where the material is a lot finer. The flow properties mean that it's more cohesive. And you can see here, we've still got pyramidal outlets, but you can see how dramatically steeper those conversion angles are to try and prevent the material from being held up inside the vessel. So basically, when we think about core flow vessels, which obviously have the preferential channel, they could fall into either conical types, as we see here, or pyramidal types. But essentially, any shape of vessel that has not been designed for a particular type of material will be core flow as a default. So virtually probably about 95% or more of the silos used in industry are actually operating in core flow. Whether or not the end users are aware of this or not, of course, is a different matter altogether. So here we've got another typically abused silo. So we've got an internal polish on this that's been put on by the equipment supplier, and they've put it on here in a direction that's perpendicular to the flow of material. So what they've actually done here is to make the surface the roughest surface you could possibly achieve. So they've actually made things far worse by applying what they might call a polish. So what we really need are bins that can operate on a first in, first out basis. This is known as mass flow, but you can only achieve this geometry by doing flow property designs, flow property measurements and designs based on those flow properties, all of which is outside the scope of what I can cover today. Hopefully I'll get invited back and we can talk about that some other time. So mass flow gives you first in, first out. Obviously no stock, no contamination between batches. It's got a lot going for it. Now, in terms of particles, so whether you've got harvested grain or other materials, the chances are that you might be handling this through pneumatic pipeline at some point. So I've got a short section here on pipelines, and the thing being is, whatever you do, never ever have a pipeline that's inclined. It's one of the worst things you can do from a reliability perspective, because the pipeline sets up a condition that's neither vertical nor horizontal, sets up turbulence, and you'll find that you've got an increased incidence of the pipeline blocking. And of course, the way that people get around this is to try and put more air through the pipeline so it doesn't block, without understanding that actually it's the pipeline layout that's the key problem. So clearly more air means more velocity. And if we have more velocity, then we get higher velocity impacts between the particles and the bends, and we get more breakage. And this breakage could be as dramatic as the complete destruction of grain, or it could just be something. It could be something like delaminating the husk off. But we can see that for different impact angles, from here 10 to 35, you can see how the particle sizes diminish as velocity increases, and you can see how the finer content increases as a function of increased impact speed. So basically, the debris created from the larger impacts migrates into the finer sizes, and you get a material that's more dusty, but also more prone to segregation. So particle breakage for harvested materials is a major consideration. But also you can get breakage through inappropriate transfer belt design. So here we've got an example of a transfer belt coming onto a cross belt down the bottom here. And you can see what we've got here is what's known as a hood and spoon. So the hood intercepts the trajectory of material coming off the top belt, focuses it down, and introduces it into the spoon section, which then lays it onto the transport belt. And this is a way of minimizing impact damage, but also it's a way of trying to contain dust into the product so you don't get huge dust handling problems at transfer points. Also, free fall breakage height. Free fall breakage can be a problem. So here we've got a telescopic loading chute. Clearly this is for an open stockpile, but the principle is interesting in that the chute is fully extended to the ground level. Material backs up, so you've got a conveyor belt up the top here, backs up to a high level, and then the chute is slowly retracted. The material spills out the base while the free fall height is contained within the upper part of the telescopic chute. So again, you're controlling breakage, but also importantly, you're controlling dust emissions by keeping the dust wholly in amongst the bulk. Same sort of thing here, helter-skelter loading chute. Same thing again, we're bringing the material down in a high density condition to try and keep the fines in with the coarse. Cascading bucket arrangement, same sort of objective, a dense flow rather than a waterfall of material going in the, in this case, the ship hold. But equally, if you were loading into a flat store, this would be something that could be of interest. Segregation, very much a problem with a lot of material, particularly once it becomes degraded. So in this case, we've got a bin that's been filled centrally. This could just as easily be a stockpile on the floor, by the way. And what you'll find is that the finer, less mobile material tends to concentrate under the fill point, and you get an absence of that content at the periphery. So this could be the edge of a heap on the floor, or it could be a region, as shown here, constrained within a storage vessel. But basically, you've got a lack of homogeneity from the center line to the outside. Loading in pneumatically, we get material contacting on the inside surface of the bin. Deceleration through friction, which then means you get an inward heap formation, whereby fines now dominate the outside, coarse now dominates the center line. Loading vertically downwards into bins, so it's a sort of thing you often find with external silos loaded by road tankers. Very normal that you get a high velocity gas flow down through the loading pipe, interacting with the bulk solid, and then that gives you a high level of turbulence in the headspace, which then particles then settle out according to their settling velocity, and you end up with a fines enriched crust on the top surface. Clearly, if this is an external silo and you've got high humidity developing in there, you've got a high surface availability to absorb humidity, and then of course you can run the risks of a crust formation. Loading in across a bin. Here we've got material loading in. Bear in mind the entry velocity here is going to probably be about 26, 28 meters a second. Impacting on the opposite side of the bin, falling back under the load point, and now we've got a very long angle of repose with high fines on the impact face and high course under the loading point. again. So you can see something as simple as putting the material into a silo has an enormous influence over how that material is deposited. And if we then think backwards to this central flow channel business, you can now start to understand why that central channel pulls out different regions of materials at different stages during its discharge. So some people try to minimize these effects. So here's a gravity fill with a distributing cap. The idea being the material falls onto the cap and you get a double angle of repose. So by shortening the length of the slope, you reduce the segregation to an extent. In theory, this is how it works. So the fines, instead of being a strong band down the center, now get distributed. In principle, it works well. In practice, it depends how intelligent you are. So here again, handling a coarse animal feed here. And so we've got the inverted cone installed on the center line of the bin. Out of view up here, we've got a belt conveyor. And of course, the installers didn't take into account for 1 minute the trajectory effect coming off the end of the belt. Hence, the material impacts off center, and rather than distributing within the bin, actually projects across to give you the worst possible type of surface effect segregation. So it's actually made segregation worse by projecting the fines over this side and the coarse rolling down to this side, simply because no thought was given to the bit of process equipment before the silo itself. Coming towards the end now, this is just another example of segregation where we've got a rotary valve up here, diverter, 2 bins packing out material. One bin had a much worse segregation than the other. The client couldn't work out what on earth was going on there. But of course, if you look at the system, you can see that material coming down the duct and passing across to this direction barely decelerates at all. So you get a very strong trajectory at this point, pushing material off to one side. So you've got stronger fines this side, stronger coarse that side. But of course, with the diverter in the opposite direction, you get impact deceleration, loss of energy, and thereby the trajectory effect is much reduced. So you don't get as severe segregation. Simply a function of the way that the chutes are laid in. But again, you know, because in industry, often the bulk handling equipment is just laid in as a connect this piece of kit to that bit of kit, and there's not much thought given beyond that. That's where a lot of these problems come from. So I think I need to be wrapping up now. So my parting comments to you are going to be that, you know, if we look back in time to the time of the Egyptians, and in this painting, we can see people working with grain that's stored on the ground. This is the way that it was dealt with back in Egypt. So that's, you know, 1000 BC. And just to prove to people that not much changes in this world, really. Here we are, 2000 AD, and we're still working with grain on the ground. In this case, it's because there was the structural loadings on this bin hadn't been correctly assessed for the material that's being stored, and it just simply ruptured itself. So in closing then, many bulk solids problems, whether it's discharge, whether it's spoiling, whether it's deblending, it's a result of the use of standard designs of construction, standard designs of equipment, which actually aren't optimized for anything, but also handling systems that are also not very well set up either. And these are usually due to a very tightly controlled and restrictive capex allocation for purchasing the equipment. So again, usually the cheapest equipment tends to win through. Key problems that affect not just agricultural sector, but all sorts of sectors, things like wear, lump formation, particle breakage, segregation, discharge reliability, material hang up inside vessels, I mean, there's a lot more I could add to that list, but they're the most typical ones. And hopefully the parting ray of hope I can give you is that there is no black magic to solving bulk solids problems. You know, equipment suppliers might make out to you that actually the only way you can deal with this problem is to buy their most recently available aeration panel, vibration panel, pneumatic hammer, or whatever. Discharge aids don't deal with the problem. They're like sticking plasters. They don't deal with the problem. But the techniques have been in place since the early 1960s to predict the storage and discharge behavior of bulk materials. So to be honest with you, the only barrier to adopting best practice, I would argue, is actually an awareness of what best practice actually is. And hopefully, hopefully this presentation just gave you a very quick snapshot of maybe some things that you may not have been aware of, but I hope you found it useful.
Thank you very much, Richard. So there's a question from me to start with, and the second question is similar as well. So my question is about CFD. So CFD analysis is used in fluids and airflow. Is it also used in bulk solids? Obviously, the big variable is the particle size and the shape.
Well, the only at this point in time, with computing power as it is, there are very useful applications of different sort of CFD type projects, and like discrete element modeling and this sort of thing are used very successfully to deal with things like transfer chute design. So you'll find that there's a lot of companies use DEM to model transfer chutes for bulk handling systems. But with regards to actually predicting the sort of storage and discharge behavior, it's still a very, very long way off yet. But to be honest with you, the traditional techniques to give you results in that field are they're accessible, and obviously I'm happy to give people guidance on books to read on this if they want, but it's actually not the scary science you might think. There are actually well-established techniques, and in fact most of the techniques, or the most commonly used technique, which is shear testing, has its origin in soil mechanics. Now you think about how long people have been building railway embankments. That goes back a long way. And so in the 60s, Andrew Janicki developed a methodology using the same approach, not to measure the strength of soils, but to measure the failure strength of bulk solids. So it's using a modified sort of shear box approach, is the way that things are traditionally done, where people have the knowledge to use that type of equipment.
And the second question, I haven't got the person's name because it's just a reference number, but they haven't got a microphone. Have you used programs such as Altair, EDEM to model particle flow?
No, I just measure it directly. It's a lot quicker. If we were looking at something like trying to predict a chute angle or a geometry or an outlet size for a vessel, then conventional shear testing can give you the data you need for that within 45 minutes. So it's not a long-winded procedure to go through. But as I say, at the moment, I would argue that the computational power doesn't exist at this point in time. But to be honest with you, the Luddite in me says that in order to run such a program, you still need to understand various aspects of the bulk material, like its angle of internal friction, its angle of wall friction. You need to understand its bulk density, compressibility characteristic. And by the time you've gathered that information, well, actually, you've just virtually finished the traditional approach anyway.
Yeah.
So like I say, the Luddite in me, because I admit I'm not a computational person, would say that actually you're 9/10 of the way there by the time you've got the data you need for the program.
Yeah, I could see that. Yeah, it's I think if you're dealing with water and air, it's much easier to understand as soon as you've got variable particle size and things.
If the particles are out, if the particles are out of contact with each other, that's where computational modeling comes into its own. But it's dealing with the friction between particles that's the problem. And most people that model particles, if you drill down into what they're doing, you've got a nominal virtual particle which has like a spring and damper system, a spring and damper associated with it, and you're putting all these springs and dampers together to try and emulate or simulate sort of an internal friction effect.
Yeah, I mean, there's a comment in the chat about this sounds very similar. A lot of similarities to soils. Yeah.
Oh, it is absolutely. It's very, very similar.
Have you, just before Alan asks his question, have you been involved in any mobile sort of agricultural machinery stuff in the past? Because obviously a lot of things like seed drills and fertilizer drills have got air. You know, they are bulk solids handling machines. They're pushing seed through.
Yeah, the sort of things the sort of things we've touched on. Well, I have been involved with a seed drill, but the project didn't actually. I had meetings, but the project never got off the ground. But one thing that I have been involved with related to spreading of fertilizers. And of course, fertilizers, you're looking at a wide range of particle sizes, shapes, and often densities. And of course, the trajectory that you get off of those when you're actually spreading them means you get an uneven distribution. But more critically, it's the segregation you create when you're decanting into the field equipment. Because one of the things that's true of any sort of material is you can have the best blend of dry material in the world, but the moment you handle it, it will start to deblend. It's inevitable. And so the more handling, decanting processes you go through, the more it's going to start to change.
Yeah. Okay. Alan?
I assume you mean me, Charlie.
Yeah.
Thank you. I just having to check if any other Allans are on the call. Yeah, I'm going to wear my health and safety hat as usual. There've been some pretty big explosions, dust explosions, you know, called electrostatic causes, including, I think, multiple fatalities in one. HSE, I don't know if they're prosecuted on it or they're going to. A big one, wasn't it? A mill up in the north somewhere. The design elements that you've been talking about, can they reduce the likelihood of that happening, or do we just have to assume because products, you know, granules, whatever, are charging around and getting all excited electrically, as it were? It's an inevitability, so it's explosion relief you've got to go for.
Well, the thing being is that there's always going to be a risk there. I mean, in one respect, you could argue that if you've got a vessel that draws down preferentially, then in effect it's it's almost an open system. So you know you're obligated to have an ATEX compliant rotary valve at the bottom of it. You could argue that if material is coming down as a plug on top of that, you've got additional depth to protect the process before that point. So some people might say it's a bit of a tenuous argument there, but clearly if there's been a you know, if it's compliant with DSEER and ATEX, then there should have been an evaluation as to the likelihood of a dust cloud anyway. So best practice, I would say, is not going to eliminate that risk, but it will bring the amount of fugitive material down, but it may still be in the exposable limit anyway. Arguably, best practice just makes life easier with the housekeeping insofar as you don't have so much fugitive material spilling out onto rotary valves or motors that needs cleaning off. I think that would probably be my maybe a bit simplistic view on it.
Yeah, That's what we need, simplicity, but no, it's fine. Thank you.
Okay.
Well, thank you, Richard, for giving us an excellent presentation and taking the time out to do so today. It is very much appreciated. I'm sure everybody found it extremely interesting. I'd like to thank everybody for joining us today and hope you will join us for our next lecture on the 15th of March, where we will be joined by IAgrE member Marion Perrett-Pearson, who is going to talk about agricultural science in the Caribbean, which all sounds very nice. So all that's left to say is thanks again for everybody for joining and see you next time. Bye-bye.